Okay, so we are moving on to section 3 of unit 7. We're looking at margin of errors and paired procedures. Okay, and so we're looking at paired data in this case. So let's start off talking about margin of error with means. Okay, because, you know, why not? All right, so let's say we have a researcher who would like to estimate the cholesterol level, blah, 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 and a type of monkey doing lab experiments. They want to be within 1 milligram per deciliter, okay, mgdl, of the true mean at 95%. Previous study involved monkeys suggested that it was the standard deviation was around 5. Okay, so the reason why you would want to know how many to sample is because of cost. That's the big thing. You don't want to, if yes, you could take 600 and you'll probably be within that one, but it's going to cost a lot. So you want to find approximately how much are you going to need, because like that last thing, it is expensive, could be time consuming, um, whatever reason. So you want to minimize the number that you need. Okay, you want as close to get that 1% or 1 milligram per deciliter estimate for your margin of error as possible. All right. So that's why we would need to know what the margin of error is. Okay, so a margin of error of 1, right? A 95% confidence level, okay, with a z, which means it's going to be about 1.96, okay, 1.96. The standard deviation was 5, and we're trying to find the n, right? And using our formula of z times sigma over square root of n, okay, we want to set that equal to 1, and then we go through and we solve for n. Okay, 1.96 times 5 gets you 9.8, which is interesting, is equal to the square root of n, and then you would square both sides. Okay, and so basically, a quicker formula, if you want to think about it this way, is that it's going to be z times the standard deviation all over the margin of error squared. Margin of error squared, whatever it is, whatever you get from z times sigma all over me, you square that number, and that's going to be your n value. So in this case, 96.04 is the n that we would want, but because you can't have 0.04 of a monkey, you would round up to 97. You always want to round up because you want to be more more sure about it. So you always increase it by a little bit, and that will actually shrink your margin of error, so that if you do say it's at 1 and people do your math, they go, oh, well, actually it's less than, you're just being more sure. Boom, got it. So 97 monkeys. Okay. So again, z times sigma over me squared, the whole thing squared, will tell you what the n is. All right, matched pair. So that was the margin of error. Let's go on to matched pair because it's important. So matched pair is basically when you take a study and you're looking at the before and after of it. So you have the same people or same objects, and you have data taken from before and from after. And with that, you're basically looking for the difference between it. Okay. You want to see, was there a decrease? Was there an increase? Did these people lose weight? Was their cholesterol level lowered? Did they have more energy, etc., etc.? And so with these, you're usually going to be using a T. Okay, it's going to be a T procedure for your inference, and we use mu sub D. Okay, mu sub D, which means the average difference. Okay, and this method is known as the matched paired procedures. All right, so matched pairs procedures is what it's called, and you can mention that under your plan, your setup, whatever you want to do. Okay, so let's look at an example with matched pairs. Okay, so there's second, blah, blah, blah. Information. Key things that we have here that we want to look at. They basically are looking to see if the express lane is faster, or if the express lane and the regular lane have a difference in time and their wait time. So these are their wait times in seconds. They did it 15 times. They randomly selected the time of day when they were going. One would be heads, one was heads, they would go to the express, the other one would go to the other one, yada, yada, yada. So it's just a lot of setup here. I mean, you can read through it if you want for all that. And we want to know, is there a difference in the significance? Okay. In the examples. Okay, so a whole bunch of information, and basically it's setting everything up. Now, what we need to find here is that we need to find the differences, okay? We want to find the difference between them going at the same time but in different lanes. And so we need to find, the difference between 337 and 342. Now, you can go through and you can subtract every single one of these and get your numbers. That's fine. The problem is that under the AP exam, when you have a time limit, it might take too much time. Now, your calculator can do this fairly quickly if you're comfortable using your lists. So if you use your list, which is under Stat Edit, you have your L1, L2, and L3. You're going to use all three of them. Under L1, you're going to type in the express lanes in this example. So under L1, you type in all of the express. Under L2, you're going to type in all the regular lane scores. Make sure they match up. So make sure 337 is with 342. Make sure 357 is with 263. So make sure they're matched up. You're going to arrow over and highlight L3. So not just on L3, you're going to arrow up so that L3 should be dark around it. And you are going to type L1, second 1, minus L2, second 2, and then push enter. And when you push enter, it should get all those scores for you. So all those subtractions. And then you use your 1-bar stats, change your list to L3 instead of L1, frequency still 1 or 0, whatever you want to put, or blank. And then that's going to tell you your new standard deviation and your new mean, okay? In which you want to make sure you use the S, the SX, not sigma X, you're using SX. Okay. All right, so under state. So under state, we are going to have the sigma, or the mean. So we state the mean, which is the difference between the express and the regular. Okay, so if you decide to go the other way, you would want to say that you took the difference between regular and express. But since I did express minus regular, that's what I'm staying there. They were just talking about the difference between it, so it's equal to and not equal to. Okay, for my null and alternative hypotheses. Okay, there you can also mention your n. Your n is 15. Your mean was negative 42.67, and your standard deviation was 84.02. Under plan, randomly selected times and assignment, it said everything was random. You assume that one lane doesn't affect the other to make it independent, and it's less than 30. You want to check the graph to see if there's differences, and then it appears to be semi-normal. Okay, so moving on to our do category. So under do, it is going to be a T. So we would set it up. We would have our negative 42.67 minus 0 all over the standard deviation that was found, which was 84.02 divided by the square root of 15. So make sure you do that calculation first. And we end up getting our number as a negative 1.96. Okay. The degree of freedom is 14, because remember it's one less, and then we want to find our p-value. Our p-value, which you would take if you used your calculator, TCDF of negative 1E99 comma, -1.96, comma 14. Push enter. The number you get, you have to multiply it by 2. Okay. So we'd have to multiply it by 2 because we are dealing with a two-tail. So when you're dealing with a two-tail, you've got to multiply by 2 to cover both sides. We get a p-value of 0.07. Okay. Another way you could do that calculation on your calculator is doing a t-CDF of -1.96 to +1.96, comma 14, and then taking that number and subtracting it from 1. Okay, and then you would see what your p-value is, which is 0.07, or 0.07, which is greater than our whatever our alpha is. Actually, it doesn't say in the problem what our alpha was. So you can state the alpha that you want. And I think at the beginning, look. Oh no, we did not mention what the alpha was. Usually 0.05 is a fairly common alpha that you can use. So whatever the alpha was that you wanted to use, 0.05 is common. If it doesn't state, then you can pick. And for the most part, pick 0.05 is what it will be. But a problem like this probably wouldn't occur because they would give you what the alpha is. So since 0.07 is more than alpha, we fail to reject. That means that we don't have convincing evidence that there is a difference between the lanes. All right? And that is it for this section. We will be moving on to section 4 next.